Kim. Kim is the lead of the Homomorphic Encryption team at CryptoLab, and his team has been working on the development of the HEaaN library for the CKTest scheme. And in this talk, he will introduce an add-on to this library called the HEaaN.Math. Yeah.
Hi everyone. Welcome to my talk. Okay, thank you for introduction. Thank you for inviting me, this wonderful community. Actually, I met a lot of people today. I couldn't meet before in person because of the COVID situation. Yeah, it's now time to remake our community again. Okay, as he introduced, my title today is a tour of HEaaN.Math. It's a kind of an add-on to the core part of HEaaN library. So here is a brief table of contents today. So I will talk about what HEaaN.Math is and what is included here, and what are main challenges for developing this kind of some special library on top of the HEaaN core part. And after that, I guide you through some kind of sceneries to look at some functions already developed in HEaaN.Math. So I choose 3 functions. So first one is multiplicative inverse, and wide functions and sorting algorithm. So basically, the reason I choose these algorithms is that it actually shows our struggle to overcome this kind of main challenges I'll talk about later. And I'm going to tell you some of our future plans. Actually, one, and after that there is something. Okay. Okay, so HEaaN.Math is actually an add-on to the core part HEaaN library. So, and it's basically a missing link between the core part FHE operations and the applications. So what I mean by that is the core part HEaaN library is here. So it's basically providing basic arithmetic operations such as addition and multiplication, rotation, and of course bootstrapping, because we are doing all FHE now. And on top of this core part HEaaN library, we have HEaaN.Math. Actually, HEaaN.Math provides a lot of mathematical functions and numerical functions. It's actually we need to do a lot of function evaluations in a homomorphical way. So basically, we approximate them by polynomials and do the computation. And we also have some other numerical functions, such as a comparison. It's one of the very important feature, because actually there are a lot of branches in the typical programming, and actually one way to provide this kind of branching programming is to provide a comparison and stuff. And also there are some sorting functions in there. And on top of that again, the HEaaN stack, it's kind of a spoiler alert, because tomorrow it will be announced formally. But it's HEaaN stat is of course provided the statistical primitives such as mean values and variances and covariance and something like that. So as a perspective of the developers of the HEaaN.Math, we are in a kind of the middle ground. So we are basically need to be very familiar with our core part FHE libraries to use flawlessly in our development of the HEaaN.Math. And we also think about our users, for example, the HEaaN.Stat, to provide sufficiently accurate and sufficiently fast APIs to that. So that's our struggle here. Okay, so I briefly list up every functions included in the HEaaN.Math. So basically we can divide them into these 5 parts: numerical comparison related, and mathematical multiplicative inverses, activation, mathematical functions beyond polynomials, and numerical sorting. So for example, for comparison, there are sine function. This is the mathematical function gives +1 if the value is positive and -1 if it's negative. And based on the sine function, we can derive the other comparison-related functions such as discrete equal, min-max greater than its name suggested. Discrete equal is test equality, and min-max is the min-max, well, the getting minimum value and maximum value, and the greater than is a comparison operation. Sorry. And there are two kind of inverse functions. I'll talk about it later. And also we have activation functions. These are mainly for our CNN deep learning applications, sigmoid value and sigmoid wide, and some mathematical functions and numerical sorting. Okay, so here are our main challenges. So first and foremost, the most important thing is we are basically doing data oblivious computation. This means that the program execution should not depend on input data. Of course, because we are mainly doing everything in encrypted manner. So it's very, but if you think about that in the user programming practices, looking at the data is very common, and we need to avoid it somehow. And the second thing is controlling approximation errors, because the core part of the HEaaN library or any other FHE is basically arithmetic functions. So we need to do such as mathematical functions beyond the polynomials, such as logarithms, exponentials. But we can do this only by approximating by polynomials. So, and actually the polynomial approximation is not complete, far from complete actually. Yeah, so approximation errors are usually far more dominant than the inherent noises of the CKK scheme or the errors from basic FHE operations. Okay. So I am now going to show you three kind of functions in the HEaaN.Math. So first one is the multiplicative inverses. So a usual algorithm is a so-called Newton-Raphson method. This is kind of iterative algorithm to find the inverse. So basically, if I give you x, then you need to give me x inverse. But there are no known globally convergent iterative algorithms. That means that we need to choose basically the algorithm goes like this. So you need first to choose the initial guess, and if there are some kind of mathematical recurrence relation, and doing that iteratively to get the inverse finally. But there are no known globally convergent algorithm. That means that we need to choose the initial value very carefully. So, and the behavior of this algorithm is very kind of differ from one with input value is less than 1 and one with greater than 1. So we have no choice but to provide two separate APIs. So we have two inverse functions, the greater than 1 and less than 1. So this is usually for ease of use for our users, HEaaN developers. Yeah, so this one is an example. And we also have wide functions. This is for an example is a sigmoid function here. So the sigmoid function is, of course, it's not a polynomial function, and we also provide two kind of sigmoid functions in our HEaaN.Math. The reason is this, because we are doing everything by approximation by polynomials, and polynomial approximation usually is very sensitive on its input range. So, for example, in this graph, if we can, our goal is to approximate this step function, but first we restrict our range from this smaller amount between in the small neighborhood of 0. Then for example, the green polynomial is one we can find. But in that case, if we give the input beyond this input range, then it could explode. So we need to find some way to kind of adjust the domain. So basically, our algorithm is a domain extension method. This is, mathematically speaking, it's just kind of precomposing some kind of domain extension function before evaluating actual sigmoid function in this case. Basically, this works like this. For example, if we have a function that only works on, for example, an interval, the interval from -1 to 1, and we need a function kind of working everywhere, for example, -100 to +100, then in that case, we can compose a function that is kind of giving -100 to 0 to the region that -1 to 0, and 0 to 100 to 0 to 1. This kind of function can be precomposed to actual computation of this sigmoid function. Yep. And it's very funny thing. The sorting is called a bitonic sort. We are using bitonic sorting algorithm here. So you can see that this kind of sort algorithm is quite exotic. Typically, we are using quicksort and a merge sort, something like that. But the major problem is this is not data oblivious design. So in bitonic sorting algorithm, the comparing elements in the predicate order, and the comparing doesn't depend on data. So basically, the horizontal lines, it means that it's a flow of the data. So the data flow from the leftmost side to the rightmost side. And vertical lines connecting two horizontal lines is actually comparison and a swapping. So for example, as you can see, this is a typical example of data oblivious design. And if we input this, then it's quite nicely sorted out. Yeah, and I'm going to tell you one of our future plan. So for example, in the large, let's assume we have a large circuit. In the middle of it is a multiplication function from multiplication with a ciphertext and a constant here. And in the case, as a developer of HEaaN.Math, we need to check the level of the ciphertext very carefully, because in the CKK scheme, we need to do bootstrapping before we run out our levels of the ciphertext. So we need to do further multiplications. So typically, this can be achieved by hands-on approach. I mean, we can check before this code. For this line, we can check whether the ciphertext is valid or it has some additional levels to say. And if it's not, we can do bootstrapping before that. But this is very hard to track down because algorithms can change and the levels are it's very hard to check everywhere. So we are doing right now we kind of need a mechanism to insert bootstrapping automatically, and this can be achieved with the help of compiler developers. We are actually collaborating with them. So you can think it's easy because well, we have ciphertext, and ciphertext has levels, and we can kind of statically analyze the entire code and then insert the bootstrapping code for that. But one of my colleagues, actually the project leader, Minjae Park, over there, point out to me that it's actually very hard because if we have a ciphertext as an input, and suppose that it is not not yet, it does not run out our level, but it just a couple of levels are left. And after the input ciphertext, we can the ciphertext can bifurcate. I mean, we can multiply by some constant and get a new ciphertext C1 and C2 and C3, something like that. Then if we insert the bootstrapping naively, then we can do far more bootstrapping than required. I mean, we can do it naively, then after C1, C2, C3 is generated and then bootstrapping. And then this kind of bootstrapping is very, very costly. So better strategy is to bootstrap before bifurcate. So bootstrap the input ciphertext first and then bifurcate to several ciphertexts. These kind of techniques are very important here. Actually, so with collaborating with our compiler engineers and compiler researchers, we are now making these kind of tests. So finally, this one is our shameless advertisement. In the Eurocrypt, we, as an affiliated event, we are doing a tutorial session. So it's tutorial sessions basically have hands-on sessions for mostly non-HE experts, but for the HE experts and for those who want more dive into this HE world, so we set two slots in there. This is basically HEaaN.Math, and you can implement it, some algorithms yourself. So, yeah, so it's April and then Eurocrypt. So if you didn't, please register and come to here. Okay.
Thank you for your nice talk. Any questions? Okay.
Thank you for the presentation. A great talk. I'm wondering, is the source code for the library available? Is it open source now? Just the HEaaN.Math?
No, it's currently closed.
It's closed source.
Yeah.
Yep.
Any other questions?
Is this currently or formerly?
I don't know actually, but we published this not a source code, but the binary version is published, so you can use it really, but it's not source code. So.
Yes.
Thank you for your presentation, and I have like a simple question. So before you start your presentation, you said that your goal is make a sufficient FHE. So I'm wondering about what is sufficient, because before your presentation, the Google team said that the consumers have tolerance for 40 minutes. So maybe you guys have kind of time limits or something else.
Yeah, that's a very great question. And as a developer of HEaaN.Math, our main job is to provide our APIs to our users. HEaaN.Stat. But actually, there is a very in HEaaN.Math. Usually, we have a very strong trade-off between runtime performance and memory or accuracy, something like that. So our strategy for now is to provide as many options as possible to the users, to they pick whatever they use. So for example, polynomial approximation is hard, as I said, but if you want more accurate approximation, then you can do it, and we can provide it. We already provide it, but it's a kind of runtime speed is kind of decreases. That's kind of thing. So, yeah.
Thank you.
Thank you. Actually, I also have some questions, but due to the time limitation, we can keep discuss later. Okay, then let's thanks to the speaker.